All right, so this is our calculus review video. And so the requests I got were to go over use substitution, chain rule, and the product rule. And I've written up here the 3 examples that I'm going to do to kind of like demonstrate those things. And then when we do the different derivative rules, we've recently used them for like a variable u of x or y of x. So I thought it would be good to kind of touch base on how that works, because thinking about u and y as generic functions is something that I've noticed can be a sticking point. But our first example was that use substitution integral. So I'm just going to rewrite it right here. The first part of a use substitution problem is identifying that you need use substitution. So sort of, I need use substitution here because I know how to integrate 2x. I know how to integrate e to the x, but I don't know how to integrate e to the x squared. So that x squared plus 1 is causing me trouble. So I'm going to say my u should be x squared plus 1. If I didn't have that x squared plus 1 up there, then my life would be easier. And then once I know what u I need to use, I have to compute du. So all you have to do to compute du is take the derivative of u, so with respect to x. So u is x squared plus 1, so its derivative is just 2x. And then you add on a dx. And then you plug these things in. So sort of I have this e to the u. That's the thing that I really wanted to take care of. And then it's going to be du, because that 2x dx becomes du. I don't know why I put it all up there. It's actually not. Pretty much done with the problem at this point. So I will write it nice and big right here. So e to the x squared plus 1 became e to the u. And then my 2x dx was du. And then you integrate this thing with respect to u. So the integral of e to the u is just e to the u plus a constant. And then you plug everything back in. So your problem was in terms of x to start, so your answer should be in terms of x. E to the u is just e to the x squared plus 1, because that's what we said u was. And the constant stays there. And that's just a general usub problem. So it's this du part that I think people struggle with. So just remember, take the derivative of u, add on a dx, and then usually it's going to be something that simplifies really easily in your problem. The next problem was that chain rule thing. So in general, a chain rule is going to be when you have like d dx of f of g of x. That's going to be g prime of x times f prime of g of x. Would be like the formula that somebody gave you. And so for this example right here, the tricky part is kind of seeing what like f and g are. So g, the function that lives inside our chain rule, is x squared plus 1. And f is e to the x. And those arrows are uneven. So we're sort of saying this is f of g of x because it's e to the function x squared plus 1. So there's g of x, and here's f of g of x. And once you've identified what f and g are in your chain rule problem, you can go ahead and just follow your formula. So you take the derivative of your g function, which is going to be 2x. So you take your derivative of g prime, 2x, times f prime of g of x. So f prime is e to the x. I guess picking exponents wasn't the best for demonstrating that. But you still plug in g. Maybe I'll do that in 2 steps. So that's your g prime. Here's your f prime, where you need to plug g into the input of your derivative for f. So it's e to the g of x. G of x was x squared plus 1. So it's 2x e to the x squared plus 1. And that's not surprising because we just found that in our example right here. So it all lines up since derivatives and integrals undo each other. And then the last example was going to be a product rule example. We'll go back and kind of show how this is related to use in a second. But the last example was a product rule example. So the product rule is just d dx of f of x times g of x is f prime of x times g of x plus g prime of x, too many parentheses, times f of x. So again, for this, our first step is going to be to identify those x's and g's. So f is e to the x squared plus 1, and g is 2x. So g prime would be 2, and f prime we found over here is 2x e to the x squared plus 1. And we can go ahead and just use our formula from here. So f prime, 2x e to the x squared plus 1 times g of x is 2x plus g prime is 2 times f of x e to the x squared plus 1. I'm going to go ahead and underline the different parts here. So here's our f of x. Here's our f prime of x. And then here is our g of x. And then our g prime of x. Like that. That's where all those different pieces came from. So that's the product rule. And then real quick, what I wanted to do is go back over these two derivative rules and kind of put them in the context of the stuff that we've been doing in class. And I'm just going to need a little bit more room to do that. Okay, so for the chain rule, I'd like to look at an example we saw recently where we were taking like the derivative of the square root of u. What's important to remember is that variables like u or y are functions of x. So they're kind of like this g of x right here. So our g is u, and our f is sort of some function to the 1/2. And so our f prime would be 1/2 x to the minus 1/2, but our g prime would be du dx. Because u is a function of x, we don't know what u is in this example, but we know that it changes with x. So then if we wanted to take the derivative of u to the 1/2, we would just apply our chain rule. We would put our g prime up front, du dx, and then our f prime, 1/2 something to the minus 1/2 power, but we would plug in our g of x. Actually, I'll do it this way again. There's our g prime of x, there's our f prime of something, but we plug in our g of x to that something. So we've got du dx 1/2 u to the minus 1/2. And I think we did something similar to that recently. I couldn't remember exactly what it was, but chain rule came up in that context. And then similarly, I can't actually remember what I said we would do here, d dx of ux. We've been doing d dx of ux a lot recently for our substitution problems. So d dx of ux, here we're going to be saying that like f is u and g is x. So g prime is 1, and f prime, since u is a function of x, is du dx. And so when we do our product rule of this derivative, we end up with f prime du dx times g x plus g prime 1 times f of x u. And we would use this to solve for du dx a lot. That's why it came up recently. So those are the things that I got requests for a like little review calculus video. People didn't ask about the use thing, but I thought that would be nice to touch on real quick. Another thing that I've seen a lot of, I guess kind of a bonus, would be trouble with natural logs and exponents. And not as far as calculus goes, but just like the algebraic rules for these things. So you might want to remember that ln of a plus b, ln of a plus ln of b is the same of ln of a b. Ln of a minus ln of b is the same as ln of a over b. And b ln of a is the same as ln of a to the b power. Those are some natural log rules that can sometimes make like finding solutions easier. And then exponents, e to the a plus b is the same as e to the a times e to the b. We use that a bit as well. And I guess that ln of e to the a is just a, or e to the ln of a is just a. Those two functions undo each other. Yeah, I think that those, like when you use this one a lot, when we have like e to the x squared plus c, and then you're like, oh, that's just c e to the x squared. Hopefully that just starts to become natural, being able to call those rules back. I'm also going to make the exam 1 review video, so you can go ahead and watch that as well.